You can see it actually being wary of the ball, the bubble ball, which is kind of a good thing, kind of giving it as wide a berth as it can as it sneaks into the corner. It looks a little like fear, but it's not. It's not actually afraid. But just to show you that it really is avoiding the ball, this is a very bad trial where it started off and the ball was actually in its way. You can see it's going away from the goal. Why? Because it knows from experience that the bumbleball will wander out of the way, or at least so it thinks. Every time it sees an opening in the defense, the stupid ball keeps bumbling in the way. Let me try down. Oh, well, get off of me! I'm losing points for this. Ah, wait, I've got an opening! I've got an opening! It's going to go for it. It's going to go for it.
I think a better algorithm.
This is one trial out of many. Most of the time the ball was completely oblivious, but here it really looks like it's an adversary. The dog is... Oh, the other thing to point out, I don't know if you noticed, the dog's walking what I would describe as backwards. But you have to keep in mind that it's not using its nose camera anyway. So it just turns out that it knows better than we do how efficiently it uses all the different gates. And for whatever reason, it made better progress to the goal using the backwards gate than the forwards gate. There was a little bit more deliberation in it, I guess. So it's always fun when it does something that we wouldn't have done. If we programmed it by hand, we wouldn't have made it go backwards. But it made perfect sense. So you might say, and I think it would be reasonable for you to do so, that giving it this independent structure in the form of the DBN, maybe he's not cheating per se, but it is giving a lot of the game away. It doesn't seem as much like learning anymore, and I think that's sort of fair. The approach that I just described in continuous domains had been used by Kearns and Kohler in discrete domains, so there was some precedent for it, but the DBN was really given. And in their paper in '99, they say specifically there's many interesting problems. The most intriguing one is how can you learn that structure from experience? The integration of these ideas with the problems of exploration and exploitation, which is what I've been talking about, is far from trivial. There's an opening right about there. But it turns out that given this kind of quick learning setup that I've described, if we can quick learn a DBN structure, we have an algorithm. We just plug that into the RMAX, the quick RMAX structure, and we're done. We have an efficient algorithm for learning without the DBN, learning the DBN on the fly. So it turns out the structured learning problem does have it is difficult. I think they were right to say that it was non-trivial. When you don't know the structure, keeping statistics on the probability that such and such will happen condition on, well, I don't know what to condition on. So it's tricky. But what we ended up discovering is that there's a quick learning combination algorithm we call noisy union, or sometimes the K-meteorologist problem, that says if at least one of the learners actually has the right dependent structure, then we can figure out which one is right and listen to it. And so the essence of it was basically, initially you have all the different structures that you might care about, and then as you're learning, you're kind of crossing ones out that you discover aren't good predictors of how transitions work, until there's just one left. And under this assumption, that one has to be right. And so you can actually, here I have it written in this kind of composed quick learning notation, but this is now, at the very bottom, it's learning probabilities, but this is embedded in something that's doing the input partition idea that I described before. Inside of that is the cross product idea, because there's multiple output dimensions, and wrapped all the way around that is this noisy union idea that's deciding which of those combinations is actually right. Because we have this nice modular quick learning framework, specifying an algorithm like that is really easy, showing that it actually accomplishes what we wanted it to is really easy, and we actually are learning the DBN structure from data. So here's a concrete example, unfortunately not a real-life data example. This is an artificial stock price decision-making, buying and selling example. We actually used some real stock data at one point. Real stock data is really hard. So it wasn't very predictable at all. I don't know what people think they're doing when they're trading stocks. But anyway, so we made up a fake one that was exploitable. And the basic idea is that the different features of the market, each feature depends on only a small number of other features. So that's a critical component for it to be able to apply an algorithm like this. It doesn't have to know what depends on what, but it has to know that there's a very small dependence, and it's searching for which are dependent on which. So we compare them in this problem. This is cumulative reward. This is regular RMAX. It doesn't know anything about the structure. And it starts off with not a lot of reward, maybe even losing some money. But eventually it figures out what to do, and then it's consistently gaining money. On the other hand, factored RMAX is we tell it the independent structure and it just has to learn the parameters of that structure, and that one starts making money really, really fast. This looks like as if it knows everything, but in fact there is this little very short time period in the beginning where it has to estimate some of these probabilities, which again it's doing with a quick learning approach, but it's exploiting very quickly. This algorithm is actually learning the dependent structure and exploiting the dependent structure. And you can see there's a little delay as it's kind of working things out, but then boom, it's following the optimal curve very quickly. Yeah?
So when you're learning the dependent structure, I mean, I can see how you would learn that if you had an arrow missing, that'd be bad. But if I add extra arrows to a DBN, I still can represent the exact same distribution.
Right.
So how do you sort of avoid
it learns well with respect to the whatever the designer says is the maximum parent size. So what it's not doing is adding additional parents on the fly. It just assumes that the maximum is the maximum and learns well with respect to that. So if you give it too big an estimate, it's going to waste time for exactly the reason that you said. It's not going to first search the little ones and go, I've got it, there's nothing else to do. Built into this whole quick learning framework and this PAC-NDP framework is a worst case assumption that says out of all transition functions in the family that I'm considering, I need to do well. And it ends up being very conservative in that sense. It's never willing to say, well, I think I've got it now, but I haven't tried this thing over here. It really tries to search that whole space.
So if you overestimated the complexity, you'll never realize that.
Yes, that's right. I mean, you can imagine slapping something on top of this that says, once you've done the learning, now start doing little experiments that say, well, would I lose something by dropping this link? But that's it's not going to improve the bounds at all. It's only going to make things worse. We can improve the bounds other ways. We have another algorithm for doing this. Let's see how we, okay, I'm pretty much out of time, but I want to show one more video. So quickly now, this is the taxi problem again. When you were doing the taxi problem, even as a group, you had realizations and insights of various sorts, and a lot of them involved, one quote was something like, oh no, you need to go over to that thing that has the same color as the ball, right? Or you need to go over to the ball now. Ball, who's saying anything about ball? Reinforcement learning algorithms, or at least the flat MVP ones, just know about state numbers. So you would have to say something like, no, go to state 6,531, right? Which of course is, you would never think about it that way. You want to think about it in terms of objects. If this is a world that's got walls, it's got colored squares, it's got the ball, which isn't in here at the moment, and there's the taxi sort of thing. And that you parse the world in terms of that. Well, we can design a learning algorithm around that same principle, and it ends up having much more human-like exploration. It's still not as smart as you guys, but it was still very good. In fact, it learns things like this. It learns like little AI-ish looking things, like if you try to go north, and it's not the case that the taxi is touching a wall to the north, then the y-coordinate will be incremented. Right? Those are the sorts of things that it learns, which is, well, probably you guess, this sort of thing you guess without even having to try it, that walls block you. And then up goes up. But you didn't know, I don't think, on the very first move, what would go up, right? Did anybody know? It would be the orange. And some person claimed that he looked at the screen and he said, oh, I know exactly what you need to do. That thing has to pick up that thing and put it there. With A and B. Okay. You've played too many video games. And it learns that the drop action, if the passenger is in the taxi and the taxi is touching the destination, then the passenger is no longer in the taxi. So it learns rules exactly like that. The quick bound that we get for learning this class of object interactions is polynomial with the number of types in the world, like wall as a type and taxi as a type. It's exponential in the size of the conditions. So here, this is 3 things in the condition: drop, this test, and this test. It's exponential in the number of those that you need to represent things. But it still does a good job. If we compare standard Q-learning with epsilon greedy, to master the taxi domain takes like 48,000 steps, which is actually good for Q-learning. If you do flat RMAX, it takes it down by an order of magnitude. If you use factored RMAX, it actually is breaking up the conditional independences. It shaves another factor or 2 off of that. If you do it with this object representation that I just described, it's down to like 143 steps. In my experience with people, they do it in like 50 or sometimes less than that.
So how do you reward it until the task is done? How does it know it's even on the right track?
It's more or less like you guys did. You just have to explore, and then all of a sudden it ended, and so then you got the reward.
So that's the only way to know that you got the reward.
In this, there's a whole line of research in reinforcement learning called shaping rewards, also named with analogy to psychology, that says you can add little hint rewards that say, oh, there's a thing over there, it's better to be closer to that, and have it get sort of drawn through the environment. There's ways of introducing those rewards so that it doesn't bust optimal behavior. So but that's sort of external knowledge usually that gets added.
So in 140